Okay, so good evening, everyone. In today's session, we are going to look at PVT behavior of real gases. So, before going for PVT behavior of real gases, let's first have a look what we had looked at last class. Yes. So in the last class, we had looked at first free expansion of gas. By that example, we tried to have a look at why gas expands. So that was basically because of the entropy of after expansion. So the entropy change is always increasing. Entropy is always increasing. That's why gas expands. Further, when we connects two blocks together, and one is at high temperature and one is at lower temperature, so there will be heat transfer from high to low temperature. So that process is favored, and that was also checked by entropy increase, and delta S was greater than zero. Further, we had looked at mixing of two ideal gases, where we find that entropy is summation xi ln xi, where xi is the mole fraction of particular gas. So if we mix them, that entropy of delta S mixing was coming out to be greater than zero, meaning entropy is increasing. So this also suggests that mixing of two ideal gases is always favored. Then after that, we had looked at first and second law of thermodynamics. So first law stating du is equal to del q plus del w, and ds is del q divided by t. So if we combine these two equations, we get combined first and second law of equation, that is du is equal to t ds minus p dv. So u is function of entropy and volume, and energy always reduces. So du SVS is less than equal to zero. That is one condition of spontaneity. Similarly, we derived the equation of for enthalpy, that is dH is equal to TdS plus VdP, and for that also dH should be less than equal to zero. Similarly, we defined Helmholtz free energy, that A is equal to U minus Ts, and from there dA is coming out to be less than equal to zero, and dG at constant temperature pressure should coming out to be less than equal to zero. So out of this, we find that this volume temperature and pressure temperature, and in these two also, pressure temperature application, dG at constant pressure temperature less than equal to zero, that is the most practical, industrially most practical condition, and that's why we are so much concerned about Gibbs free energy. Then from that we move to Maxwell equations. So these also we had a look that du is TdS minus PdV, then del U del S will be temperature, and del U del V at constant entropy will be minus P, and we can write from Maxwell relations that del T del V at constant entropy is minus del P del S at constant volume. And similarly, we did this exercise for various thermodynamic potentials like enthalpy, Helmholtz free energy, and Gibbs free energy. And why we did Maxwell relation? That was because from Maxwell relation we can convert non-measurable into measurable quantities. Then we had some entropy relations, that entropy when it is a function of volume and temperature, then what do we get? And when entropy is function of pressure and temperature, and similarly for internal energy as temperature of function of temperature volume, and enthalpy as a function of temperature and pressure. These four expressions we derived, and we stopped, and after that we had a look at Cp minus Cv and Cp by Cv for ideal and real gas. So that is what we did in the last class. So here, one point that we had a look at, we stopped it here, is when the gas is ideal, then this dH is just CPDT, du is just CVDT. But in reality, gases are not ideal. So this part, this right hand side of the coefficient of dP, that takes care of real gas part. So how to move from ideal gas to real gas, this is what we are going to start with today. But before moving there, I would like to have a look at one sample problem that last week we could not do it. So the problem statement is this. Sorry. Okay, I have not opened it. So this is the problem statement that we are going to look at. Okay, so this is the problem statement that states that for a gas obeying the equation of state P into V minus B is equal to RT. So you know that this is not ideal gas because for ideal gas PV is equal to RT, but here V is replaced by V minus B term. So P into V minus B is equal to RT. So we are supposed to calculate enthalpy change and entropy change when the gas is taken from state 1. State 1 is P1 is equal to 10 bar, T1 is equal to 300 Kelvin, to state 2, that is P2 is equal to 20 bar and T2 is equal to 400 Kelvin. So delta P we have and delta T we have. And we are supposed to assume that Cp is equal to 40 kilojoules per kilomole Kelvin over the temperature and pressure, meaning Cp is not changing with temperature and pressure, and B value is given 0.3 meter cube per kilomole. So how can we solve this particular problem? So we had a look at this particular equation. We are supposed to find, sorry, we are supposed to find dH and ds. So what is dH? dH is just simply this equation, and when I integrate it, I can calculate delta H. So Cp is given to us in the problem statement that Cp is equal to 40 kilojoules per kilomole Kelvin, and dt is if I integrate this, dt will be just delta T, that is T2 minus T1. So my T2 is 400 Kelvin and T1 is 300 Kelvin. So my delta T is nothing but 100 Kelvin. And similarly for this part, V I know. So from equation, what can I write? V is equal to P into V minus B is RT. So V I can write it as RT by P plus B. So I can replace this V as RT by P plus B, and this term minus T del V del T at constant pressure. So del V del T at constant pressure, what will it be? V is my RT by P plus B. So del V del T will be R by P. So R by P into T. So when I put these values, can you tell me what is the answer that you should get by solving it for enthalpy change? Shruta, are you here?
Yes, sir.
Can you solve it? Did you understand what I explained?
Yeah.
Okay, can you try for solving?
Yeah.
So just use this formula. P1 is 10 bar, T1 is 300 Kelvin. Similarly, P2 is 20 bar and T2 is 400 Kelvin, and CP value is given and B value. Everything is given to us. We just need to put the value in this particular formula. So okay, I'm keeping this slide open so you can note down the data.
Yes, sir.
P1 T1 10 bar and 300 Kelvin, and P2 T2 20 bar and 400 Kelvin, and CP is 40 kilojoules per kilomole Kelvin, and B is 0.2 meter cube per kilomoles. May I move to equation slide just to show you what is the equation? This slide.
Yes, sir. Yes.
So this is the equation. You need to put the values.
So can you go back to the question slide?
Yes, sure. Be
Is it
consistent units. Yes.
answer question option C?
DH you got as 4200. We can check. So sorry. DH is coming out to be, yes, 4200. Entropy did you calculate?
Yeah, it's 5.74.
Okay, entropy you calculate as 5.74. Okay, kilojoules per kilomole Kelvin. Very good.
Yes.
So I will just complete it for sake of doing it. So Cp is given, dt is delta T. When you put del V by del T at constant P, it is R by P. So this term is only left with B, small b. So you get it like this, that Cp into dt plus B into dP. So Cp dt, when you put all the values, you get delta H is 4200 kilojoules per kilomole. Now for entropy change, this is the equation of entropy change at Tp. So ds is Cp by T dt minus del V by del T at constant pressure dP. Cp is given, dt by T, so you need to do integration. So that gives us ln T2 by T1 minus this term is nothing but RT by P, R by P, only R by P. Del V by del T at constant pressure is R by P. If you back calculate this, sorry, if you integrate, if you differentiate volume equation and into dP, so R by P dP, so dP by P is again ln P2 by P1. So this kind of expression you are left with, that is Cp, ds is Cp ln T2 by T1 minus R ln P2 by P1. So you get 5.74 kilojoules per kilomole Kelvin. Okay, so let's move ahead. So there is one more problem. Where does it go here? Yeah. So we are asked that uh, this one, this we did last time. Sorry. Uh, yes, this one. Okay. We are saying that del V by del T at constant pressure is greater than zero for real gases. Okay, it makes sense. Volume increases, temperature increases. Then for the same change in pressure, so we are supposed to choose something. One expression is temperature decrease is greater for isentropic expansion as compared to isenthalpic expansion. Second is temperature decrease is greater for isenthalpic expansion as compared to isentropic expansion. C is temperature decrease is same for both isenthalpic and isentropic expansion. So for first, what we need to do, we need to write down the expression for isenthalpic expansion and isentropic expansion. So if we take this equation, if I yes, if I take this expression, so for isentropic process, ds will be equal to 0. Correct. So Cp by T dt will be equal to del V by del T at constant P dP. So you can write what is asked to you, temperature decrease or temperature change we are supposed to find with pressure. So how can I write it down? If for isentropic, this term will be equal to 0. So my del T del P at constant pressure will be equal to nothing but this simple term. Sorry, I'll just show you the expression. Yes. So we had this for isentropic. So I just need to equate it. So del T by del P, that is temperature change at constant entropy isentropic process. That is nothing but, if I equate it, so del T del P will be equal to this term. And similar expression we are supposed to find for isenthalpic. So what will be for isenthalpic process? Same thing. This dH will be, we will be putting at equal to 0. Correct. So my del T del P will be coming out this term divided by Cp. Correct. So this is my del T del P at constant enthalpy. So this is one equation for isentropic equation and this is second for isenthalpic equation. So from looking at these two equations, can you tell that in which process volume change will be, sorry, temperature change will be more? If it is more here or it is more here? This quantity will be more or this quantity will be more? Anyone? At constant, this is also, so which one will be more? You see that this is just T del V del T at constant pressure by Cp, and this is T del V del T at constant pressure by Cp minus V by Cp. So something is removed from Same term is removed by minus V by Cp. So that's why this is more. This quantity is going to be more than this. So we can say that we can say from our problem statement that temperature decrease will be greater for uh, isentropic expansion as compared to isenthalpic expansion, correct? Because there is only one additional term, that is minus V by Cp, that is reduced from the same term. So if it is reduced, then it is giving little value, it is subtracting it, so it will be less. Is this clear to everyone? Shruta, is that clear to everyone? Is that clear to you and everyone?
Yes, sir.
Yes. Okay. So these two problem I could not cover last week. So today I finished it. So let's start with today's. Uh,
Sir,
yes, sir. Yes.
um, actually, I was not able to attend the last lecture. So, is it
Yes.
possible that you can provide the recording for the same?
Yeah, it's available on YouTube.
Oh,
Uh,
okay.
I can. Yeah, see it's here. So here, where does it go? Sorry. You're not shared that part with you that oh, I opened Creator Studio. Sorry, I wasn't supposed to open this. My videos, yeah, playlist here. So see here, you can see. So this last lecture is available here, week 2. So you can check from here.
Okay, sir. Thank you.
You can search by my name or something. You may find it.
Okay.
Okay. Okay. So
Yes.
let's move ahead to next today's topic. So today we are mainly going to focus on PVT behavior for real gases. So for that, we understood the motivation that why do we need to go for real gases, because of this particular V minus T del V del T at constant pressure terms appearing in enthalpy, internal energy and entropy in some other ways. But these kind of terms are there, and for ideal gas, this term goes to zero. But in reality, gases are not ideal. So let's try to go there. So for that, let's first start with Gibbs free energy. So in last class, we had a look at entropy as a function of temperature and volume, temperature and pressure, then internal energy as a function of temperature and volume, and enthalpy as a function of temperature and pressure. Now, let's say this is the standard equation that we derived in last week, that dg is nothing but vdp minus sdt. So if I write del g by del t at constant pressure meaning this term is going to be zero. So I am only left with minus s. So by just by changing Gibbs free energy as a temperature function of temperature, I can directly estimate the value of entropy. Entropy is non-measurable. Non-measurable is connected with a measurable quantity. Similarly, if I okay, let's do one more thing. So if I do G is H minus Ts, correct? So if I do G by T, so G by T is H by T minus S. So if I differentiate this whole equation with respect to temperature, so del of G by T divided by del T by keeping pressure constant, so I get as this term differentiating with respect to temperature H by T del by del T of H by T minus del by del T of S. So what will be del by del T of H by T? I am keeping 1 upon T constant, del H by del T minus H constant, del 1 upon T, differentiation of 1 upon T is minus 1 upon T square, minus del S by del T at constant pressure. Okay. So this term del S by del T at constant pressure is nothing but Cp, heat capacity, energy required to increase the temperature by 1 degree Celsius or 1 unit. So this is Cp by T. This term is Cp by T. This is minus H by T square. And this term del S by del T at constant pressure is nothing but Cp by T. How can you see that? See, so del S by del T at constant pressure. So this term will be zero constant pressure. So we are only left with Cp by T. So we get del G by T is nothing but minus H by T square. So this both ways we are connecting S and T with delta G, change in Gibbs free energy with temperature. Okay. Now, enthalpy change is nothing but Cp dt for ideal gas. So let's say I'm going from let's say I'm at 0 Kelvin to I'm going to fusion temperature. So from 0 to T fusion, I will need to increase the temperature, and for that energy will be required. Then when it will reach at fusion temperature, T fusion, it will not change the temperature, but we still need to provide some amount of energy. So that is nothing but delta H fusion. Then from fusion, from solid to solid to liquid phase. So that is T fusion to T boiling point, Cp dt. That is for liquid phase. Sorry, vapor, liquid to vapor. I'm sorry, liquid to vapor. Cp dt, and at that, when let's say water boils at 100, so at 100 degrees Celsius, temperature change doesn't occur, but we need to give additional heat, that is latent heat of vaporization, plus again from going from that temperature to any temperature T, that is Cp vapor. Okay, so in this whole process, similarly we can write it down for S of T. Okay, so how can I ended at some temperature h of t, and I started with temperature h of 0 at t is equal to 0. So this is my expression for enthalpy change from temperature t is equal to t, which is at and temperature t is equal to t, and we started with t is equal to 0. Similar expression we can write down for entropy also. So it is just Cp by T. Okay, here it should be T. I'm sorry, I forgot to write it. Here it should be T. Cps by T dt. Similarly, delta H fusion by T fusion will be added. Then again, T fusion to T boiling, we need to go Cp by T dt. Then delta H vaporization by T boiling point. Then again, T boiling point to any temperature, T Cp dt. So how can I write it? Similarly, delta S of T minus S of 0. So what is S of 0? What is entropy at temperature T is equal to 0? What is entropy at temperature T is equal to 0? 0 Kelvin. What does third law of thermodynamics states? Entropy at T is equal to 0 is 0. So 0 Kelvin, there is no disorder in the system. So this term cancels out. So this is nothing but S of T. So these are the two expressions. So from this, if we try to plot them, so this is H of T minus H of 0, meaning enthalpy change curve versus temperature. So first we need to increase the temperature. So with increase in temperature, this will increase. Then at fusion point, temperature is not going to increase, but only heat is required to provide. Then again, T fusion or T melting point to T boiling point, we need to increase the temperature with which energy will increase. Similarly, when it will start to boil, temperature is not going to change, only energy is required to give, and then again T vaporization to any temperature T that we want to go. Okay, so this temperature, this enthalpy is called sensible heat, and this enthalpy is called latent heat, if I am pronouncing it correctly. No change in temperature, yes. So this enthalpy where temperature change is occurring, that is called sensible heat. That heat needed to provide is called sensible heat, and this part is called latent heat. Similar curve we can also draw for S of T versus T. Now let's say I want to find now Gibbs free energy. So G of T minus G of 0. So G of T minus G of 0, what is G? G is nothing but, if we see here, H minus Ts. So G of T minus G of 0 is H of T minus H of 0 minus T, S of T minus S of 0. Correct? So if I combine these T terms and 0 terms, so H of T minus T S of T minus H of 0 plus T into S0, sorry, it should be T here, I'm sorry, T into S0, but S0 is nothing but 0, entropy at 0 Kelvin is 0. So we are only left with G of T minus G0 is nothing but G of T minus H0. Okay, so if I plot it, okay, so we know that from here that del G by del T at constant pressure is minus entropy. What does minus entropy mean? Let's say I'm increasing the temperature. So what is going to happen? Is entropy going to increase, or is slope positive, or is slope negative? Can anyone tell me? If I increase the temperature, what is G of T minus G of 0 going to be? if it is going to increasing function or is it going to be decreasing function with temperature? From this equation, can anyone tell me? The slope is negative. If I plot delta G versus T, slope is negative. Slope is negative meaning it is reducing with temperature. So this function decreases with increase in temperature. Okay, so we will, okay, I'm currently showing what is the function, and you can see that for solid, it is almost, it is very, very slowly changing than for liquid and for vapor. So why this kind of changes? Because you know that entropy of vapor is highest. So S of V meaning entropy of vapor greater than S of L greater than S of S. So vapor has highest entropy, then liquid, and solid has least entropy. Solid has least entropy, very minimum entropy. So with increase in temperature, it is not going to change significantly, but it will reduce very, there will be very little amount of change. Then for liquid, even more, and for vapor it will be very steep point. Okay, so slope is steepest for vapor and least steep for solid, and at each transition point we can calculate delta G will be 0, so delta H minus T delta S is 0, so you can find uh, T transition, or you can find this entropy changes. Okay, and this curve gives us very important details that why solid phase is favored at lower temperature and why vapor phase is favored at high temperature. Okay, so this is the same plot if I have plotted. So let's see if I am extrapolating this on this side and this on this side. I'm expanding this curves. Let's say the curve were not like this, it were like this. So let's say you are here. So what does this mean? You are here meaning this is the solid curve that we have extended. So what here mean, sorry, liquid curve that we have extended. So what does this mean? That at this point liquid enthalpy, liquid Gibbs free energy is greater than solid Gibbs free energy. So that is not possible. Similar thing also here, G of S is greater than, this is S, we are solid curve, solid line we are extending, so G of S is greater than G of L. So we should be at minimum value of Gibbs free energy. So here also this point is not favorable because it's not going to be here because Gibbs free energy is higher, so it is going to be here. So this curve also explains why solid phase is favored at lower temperature, and liquid and vapor phase is favored at very high temperatures. Okay, so if I extend this line here and here, so we see that for vapor Gibbs free energy is even lesser. So that's why it shows that it is possible, vapor is possible at very high temperatures. So these are the characteristics for G of T minus G of 0, or you can also say G of T minus H0 curve. Both curves are, the meaning is same. So when I say G is H minus Ts, so at very high temperature, entropy is very high temperature. So temperature is very high. So this is, it is minus Ts. So this will be our, this term is going to be very important at very high temperature. And when temperature is very low, so delta S, when temperature is low, then delta S is low meaning temperature is higher, and delta S is high meaning temperature is lower. So at lower temperature, this term is not going to dominate, but at lower temperature, this term is something that is going to dominate. Okay, so you are asked this kind of question at gate, that at lower temperature, entropy, enthalpic or entropic contributions are important. So you should know that at higher temperature, these entropic contributions are important, and lower temperature, enthalpic contributions are important. Okay, so again we are coming back to this equation, dg is vdp minus sdt. So earlier we had a look at del g by del t at constant pressure. Now have a look at del g by del p at constant temperature. Okay, initially we looked at how Gibbs free energy varies with temperature. Now let's see how Gibbs free energy varies with pressure. So what will be the expression? Del G by del P at constant temperature, T is constant. So we are only left with volume, molar volume or volume, however we want to say it. So if I integrate this equation, so delta G will be equal to P1 to P2 V into dP. Correct. So let's say I am dealing with ideal gas. So my V will be equal to RT by P. So my delta G is RT ln P2 by P1. So what are we seeing here, that Gibbs free energy is not directly increasing with increase in pressure, but it is increasing in logarithmic manner, that it is going from ln P1 to ln P2. It's not going from P1 to P2, it is going from ln P1 to ln P2. So that change in Gibbs free energy is in logarithmic manner. And we have already um, had a discussion that constant temperature pressure conditions are of most practical application. So this equation is very important for reaction equilibria when we are dealing with a gas phase reaction. Okay. Now, okay, so this is the same thing that we are again looking at. So this we derived. Yeah, let's say V is not directly function of, we cannot write that V is RT by P. So we are just writing some general statement that delta dg is G2 minus G1 is nothing but V into P2 minus P1. So for solids, there is no change of pressure on volume. So these terms are not going to, if I am changing pressure, these terms are not going to give any significant part for vapors and for solids and liquids. So for solids and liquid, Gibbs free energy is generally not a function of pressure. Okay. Now we have already seen that del G del P at constant temperature is volume. So my volume of vapor is highest. Vapor is expanded. So vapor has highest volume compared to liquid compared to solid. So let's say I'm willing to plot delta G by delta P. So which line will be steepest? Okay, so first let's see, will it increase with pressure or will it decrease with pressure? Anyone can tell me? From this slope is positive. So what is going to happen? Delta G of transfer is going to increase or decrease with pressure? Anyone? Slope is positive, so it is going to increase. Now, slope for vapor is, vapor volume is very high, so slope will be very steep for vapor phase. You see, very steep for vapor phase. Then similarly for liquid, it will be, volume will not be very high as vapor, so it will be not more steep. And for solid, there are very insignificant changes to pressure with volume, so it is very less changing with pressure. So this is what you can learn. So same thing you can also see here, that let's say I am increasing this line both sides. So we can see that solid is favored at very high pressures, liquid at intermediate pressures, and vapors at very low pressure. Okay, so you know this CO2, CH4, all those gases, they are in vapor phase at room temperature. So gases are favored at low pressure, very low pressure, liquids at intermediate pressures, and solids at very high pressures. Okay, so I hope this is clear. So we had a look at Gibbs free energy as a function of how Gibbs free energy varies with temperature and how Gibbs free energy varies with pressure. Okay, so is this clear to everyone? So I can move ahead. Anyone, can you please respond?
Yes, sir.
Okay, so let's take some small, I will not say them problem statement, but some theoretical questions. So, okay, we are done here. So I will, yeah. So, okay. So can anyone tell me, we just had a look at this Gibbs Helmholtz equation. So what is the correct expression? Can anyone tell me? We derived it just now. Harshit, can you tell me what will be the answer? We derived it.
Is it B?
It is B. No, it is not B. It is minus delta H by T square. But what term was delta H minus delta H by T square? It was this. D of G by T by del T. Okay. Not, sorry. Yeah. Not this. It was D of G by T. We derived G by T expression with temperature. We derivated, we differentiate it with respect to G by T term with temperature, and we got that d of G by T by del T is equal to minus delta S by T square. So it should be option E. Do you want to see derivation once again? I can show it to you. So we wrote G as H minus Ts, then G by T we wrote, and we differentiated it with temperature. Okay, is it clear? Who said
Yes,
B?
sir.
Sorry, I did not know. Shruta, did you?
Sir, I said.
Okay, okay, Mihika. Okay, so it is clear for you, right?
Yes, sir.
Okay, sir. So let's move ahead with next thing. That is this. Okay, so this we just studied. Which of the following characteristics is not exhibited by the Gibbs free energy curve as a function of temperature for a pure substance? So what can be the answer? You have a look at slide and tell me. Anyone? Which is not true. Okay, we just studied this.
Option C.
Option
Option
C, correct.
C.
Sorry.
C option.
Yeah. So let's have a look at that once again. So the function was continuous. If we see here, the function was continuous because of this term, but slope was discontinuous and it was decreasing with increasing temperature. Why? Because the slope was minus. Del G by del T at constant pressure is minus S. So slope was negative. So it does not increase, but it decreases with increasing temperature. And one more point was slope is steepest for vapor. Why it is steepest for vapor? Because slope is minus S and entropy is highest for vapor. So slope is very high for vapor. So that's why the curve is steep for vapor than liquid and for solid. Okay. Clear to everyone? Okay. Okay. Then what will be the answer for this? Gibbs free energy for solids. Does it increase with pressure, decrease with pressure, independent of pressure, or increases or decreases with pressure depending on temperature? Anyone? Anyone? What is del G by del P? Del G by del P is volume. Okay, so slope will be volume. So for solids, what is it going to happen? Is volume going to change with pressure? For solids, is it going to change? No, it is not going to change. That's why it is almost independent of pressure. Okay, this term, this slide, slope is volume, correct? And volume is least for uh, volume is maximum for solid. Okay, but the delta G volume change is not going to happen with increase in pressure. Slope is volume, so volume is not going to change with pressure. We know that. So d G at P2 is approximately G of P1. Is it clear, everyone? No one responded. That's why.
Yes, sir.
Yes,
Okay.
sir.
Then okay, I don't think more questions are there. Okay. So yeah, so we'll have to wait. Okay, so let's move ahead. Okay, so let's move ahead for pressure temperature diagram. So what does pressure temperature diagram imply? So this is pressure temperature diagram. So first there is sublimation line. Sublimation meaning solid to vapor. There is solid to liquid is fusion. This is solid to liquid fusion line, and this is liquid to vapor, that is vaporization line. Correct. So solid, this 1 to 2 is called sublimation curve, where solid and vapor are in equilibrium. Then this S and L are this line is called fusion equilibrium curve, that is fusion curve, and this 2C is called vaporization curve. Now, what is going to happen if I keep increasing the temperature with pressure? So there will be one point where liquids and vapor will be we can't distinguish them. So that point is called critical point. Okay, so before above critical point we can't, below at critical point we can't distinguish liquid and vapor. Okay, so this is PT diagram. So this PT diagram, why this curve is very steep. So this we will be seeing in next class or next to next class, where we are actually deriving this those Clapeyron equations and all. So from there you will see that why this slope is very steep for fusion and why this particular nature of slope for vaporization. Okay. So this 1 2 is solid to vapor, that is called sublimation curve. 2 3 is solid to liquid, this solid to liquid, at this is called fusion curve, and 2C is solid to liquid to vapor curve. Okay, so now you see at one thing that all three points are combining at, all three curves are combining at a point. So what is this point called? Anyone knows? Anyone knows what is this point called? Point 2, where all three compositions
Triple point.
coexist. Triple point. Very good. So this point 2 is called triple point, and triple point is invariant. What does invariant mean? That triple point can't be changed. It triple points occur at particular pressure and particular temperature, and it's a pure substance, so there is no composition term. But for pure system at temperature, for particular temperature and pressure only, we can find a critical point. So can anyone tell me what is the degree of freedom at critical point? What is degree of freedom is nothing but, can anyone tell me equation for degree of freedom? How can we find degree of freedom? Mihika, what is the equation? You know it, right?
No.
Gibbs rule, you have studied C minus P plus 2, right?
Huh. Yes.
This thing, it is open. Sorry. This Gibbs phase rule, F is nothing but C minus P plus 2. So this is F is called nothing but degrees of freedom. So how many intensive variables we need to specify? What does this mean? How many number of intensive variable? Those are independent of quantity that we need to specify. That is defined by C, number of components, minus P, number of phases, plus 2. So what will be degrees of freedom at triple point? Can anyone tell me? For this pure substance, my component will be only one. My phases will be
0.
3. So F will be equal to 0. So triple point is invariant. We cannot vary triple point in any condition. It is fixed that this particular temperature and pressure only we are going to have critical point. Okay. Now what will be, sorry, here, what will be my degree of freedom at this particular solid vapor equilibrium for a pure substance?
For sublimation.
Sublimation curve, this line where solid and vapor are in equilibrium, this line. So I am only dealing with one component as of now. So my C will be 1. What will be P?
Degree of
Uh,
freedom.
what will be my F? F is nothing but C minus P plus 2. So what do you get as F?
Is it 1?
Is it? Yeah, it is 1. So I can either vary pressure and temperature and I can get this sublimation. Similarly, what will it be for vaporization curve when liquid and vapor are in equilibrium? What will be degree
Again
of
1.
freedom? Again 1, correct. Let's say I'm only dealing with this particular phase, liquid phase. So what will be my degree of freedom in this particular phase, this part?
2.
2. What does that mean?
Purely liquid. Purely in
Yes.
liquid state.
So what does that mean? It means that if I need to specify a pure liquid phase, then I need to specify two intensive parameters. So those are pressure and temperature. I need to say, I say that water is liquid at room temperature and room pressure. Okay, so those are 2 degrees of freedom that we are saying, that at temperature and pressure we need to specify to say that this water is in liquid phase. Okay, so this is all about PT diagram. So this is called critical temperature, critical point. So critical point to corresponding temperature is called critical temperature, and corresponding pressure is called critical pressure. So anything about above critical temperature, critical pressure is called supercritical region. So what is one example of supercritical fluid? Do you know? Supercritical state, example of your air is the example of supercritical fluid, supercritical state. Okay, so this is all about PT diagram. Now let's move to PV diagram. So what does PV diagram say? PV diagram meaning pressure and volume diagram. So what happens for solid? If I increase the pressure, what is going to happen for solid? Is volume going to change for solid? Anyone, can you tell me? Shruta, can you tell me what is going to happen when I increase the pressure of solid? Is volume going to change or no? There will be very insignificant change in volume when I am applying pressure to a solid. So you see that from change of pressure from here to here, volume change is almost negligible. Correct? So this is solid line. Then what is going to happen for liquid? So liquid also behaves incompressibly. So when I am applying pressure on liquid phase, so similar thing I am also going to observe for liquid, that liquids are mostly incompressible. So volume change does not happen for liquid. It happens for liquid, but not uh, um, there will be some changes in liquid volume compared to solid state. Okay, so similar line we are getting at liquid phase. So in between, that is equilibrium of solid and liquid phase. Correct? Now what is going to happen when I am increasing the pressure? When I am increasing the pressure on liquid, it will be at one point it will convert it into vapor phase. So it converts it like this, that in this liquid I increased, this is at one temperature, so I increased the volume. Sorry, I decreased. Oh, sorry, I was asking the wrong question. I should ask what happened on decrease on pressure. Sorry, I was asking increase, but it follows like this. Okay, so what happens when I am reducing the pressure? So this is at one temperature. Let's say T is equal to T1 temperature. So this will be at some temperature T that is less than Tc. So this is my liquid phase and this is my vapor phase. So liquid and vapor will be at equilibrium. This is at particular temperature. Let's say I am doing this similar curve for some other temperature, then some one more curve at one temperature. So what is happening if I connect these all points, so I get this kind of particular dome. So you can see that as I am increasing temperature from here to here, so what is happening, the size of this dome is continuously reducing, okay, with increase in temperature. So there will be many more lines. I have not shown them, but I can add if it is possible. So there will be, I don't think I'm able to add it. Oh, sorry, here. See, if I add one more line here, no, it's not working. It's like this. So see, it will be like this. So if you connect all these points for all temperatures, so you get this kind of dome. And you see that as temperature is increasing from here to here, so this dome this height, not height, this width is reducing from very large value from here to here to a very small value. So as I keep increasing temperature, so what is going to happen? This distance of liquid vapor, this line is going to be just one at one point. So what does that point mean? What does this point mean? That okay, here what do you mean? This one is my liquid volume, this one is my vapor volume. So there is a gap in liquid volume and vapor volume. What is going to happen here? Liquid volume, vapor volume. So the gap has reduced. So what does this mean when there is no gap in liquid and vapor volume? What does that point know? What do we call that point? When we just had a look at, yes.
Critical temperature, critical
Yes,
point.
critical point. Why critical point? We just showed that at critical point we can't distinguish from liquid and vapor. So as temperature is increasing, so this vapor, this liquid, and this vapor, sorry, I'm so sorry. Yeah, so this is going to, this is at one lower temperature. So there is, this gap is more, and when I am increasing the temperature, so this gap is less. So as I go near and near to critical point, this gap is going to be less and less, and at critical point it will be only at one point where we can't distinguish it from, we can't say it is liquid or vapor, and at that point molar volume of liquid is equal to molar volume of vapor. So this is called critical point, and above critical point it is just one supercritical state. Okay, so okay. So this is solid, this is liquid, and this is solid liquid equilibrium. This is liquid, this is vapor, this is liquid vapor equilibrium. This was vapor, so this is solid vapor equilibrium line, and where all these three curve meets, this is called critical point. Okay, so okay, so this is something important for you on GATE regarding to GATE examination. So we defined X, that is called quality or dryness factor. So what is dryness factor mean? It is the ratio of moles of vapor divided by moles of liquid plus moles of vapor in this particular region. Okay, let's say I am on this side. So what is it mean? That here liquid phase is more. If this side I'm more on vapor side, and when I just crossed it, I will be converted into my whole components will be converted into vapor. So this is more on liquid region, this is more on vapor region. So for dryness factor, X is nothing but NV divided by NL plus NV. Okay, so my, when I am at this curve, this is my saturated liquid curve. So what is saturated liquid? Liquid meaning there are no vapor molecules. So NV is equal to 0. So my X is equal to 0 for saturated liquid curve, and similarly saturated vapor curve meaning only vapors. So NV, NL is equal to 0. So NV cancels out, and X is equal to 1. If I perform, this is not mass balance, but if I perform this kind of balance, component balance, so N is total moles. N is nothing but this NL plus NV. N into some volume, molar volume V is equal to NL into VL plus NV into VV. We can write it, right? So from that we get that VM is equal to 1 minus X into molar volume of liquid plus X into molar volume of vapor. So this equation is called Lever rule. So these questions you may be asked in GATE examination, that you are given liquid and vapor phase volumes, total volume, liquid volume, and vapor volume, and you are supposed to find the what is this dryness factor. So this is what, how you can derive it. So this lever rule, volume, molar volume at equilibrium is nothing but 1 minus X into VL plus X into VV. So this similar thing we can also write for enthalpy, entropy and internal energy also. So the equations are similar: 1 minus X into whatever property I am looking at in liquid phase plus X into whatever property I am looking at vapor phase. Okay. So I hope this part is clear to you. Is this clear to everyone?
Yes.
This PV diagram and this lever rule. Okay, now we had looked at this is the curve that we obtained. Okay, and this will be my liquid volume, this will be my vapor volume. And what I did, I actually in last slide, I just drawed it as a straight line. But in reality, it is not a straight line. Okay, so when this line touches this, this is my vapor volume, and sorry, this is my liquid volume and this is my vapor volume. So but in reality this is not a straight line, it follows like this. So what does this mean when it follows like this? So when I'm going from here to here, let from my this transition to this transition, what does this mean? Pressure is also increasing and volume is also increasing. Is this true behavior of any gas that pressure and volume both can increase simultaneously? If you just see ideal gas law, if pressure and volume both are directly proportional or both are inversely proportional to each other, pressure and volume
Inverse.
uh, inversely proportional. What does that mean? That means that if I'm increasing pressure, my volume is going to decrease, or if I'm decreasing pressure, my volume is going to increase. But the curve is not like that. The curve is saying that pressure is also increasing and volume is also increasing. So here at this particular point, we get one more root of this whole equation, that is V2, or that is third root. And in most textbook, they call it as insignificant root, because this whatever volume we are going to get from this calculation, it is not going to make any sense. Okay, so this is the in reality, you should just remember that in reality the curve is not a straight line, it is like this, and this third root is not significant because pressure and volume both increases, uh, both it is showing that both are proportional, not inversely proportional. This is not something we can achieve. So this is something that you should remember. Okay, so we will see some example, we will see some equation of states in upcoming slides. So before going there, let's discuss this disappearing meniscus experiment. So can anyone tell me, you have already learned it, so what do we do in this experiment? How do we, why is that experiment, for what we use this disappearing meniscus experiment? Can anyone tell me? It is for measurement of, Harshit, can you tell me what is the use of this meniscus experiment?
Measuring critical point.
Yes, it is used for measuring critical point. Okay, so what do we do in this experiment? This is the method, classical method to determine temperature and pressure. Okay, we had a look at one particular very property of critical point. What do we know? That molar volume of liquid and molar volume of vapor are same. We can't distinguish them from each other. So these also we looked at here, that this is my critical point, and critical point there is no distinguish of liquid and vapor. Okay, so that is the key principle that we are going to obtain. So we fill liquid in a tube. Okay. We fill first liquid in a tube, we heat it and we seal it, so under some high pressure vessel. Okay. So what is going to happen when I am increasing the temperature of liquid? It is going to start vaporizing. It will be in first this region. It will be, sorry, I should be here. So as my temperature is increasing, so this was one line that wait, he will show you. Yeah. So let's say as I am temperature increasing, so I will go from this temperature curve to this temperature curve. Then again, if I am increasing, I will go to this temperature curve to this temperature curve. So what is going to happen when I am increasing the temperature? This difference in vapor and liquid volume is going to reduce, and there will be one point where there is no difference in liquid and vapor volume. So how are we going to So it is as simple as that, that when the liquid and vapor volume are going to be same, then that will be our critical point. So in experiment, what is going to happen? Liquid and vapor are there in equilibrium. So there is some, those are phase separated. So that phase separation is, I can't, that is represented, that is shown by some meniscus. So what is going to happen when my temperature is increasing and increasing and increasing, and I am reaching here, so there is no distinguishment of liquid and vapor, so this meniscus disappears at that point. So the point at which the meniscus disappears, so that point is called critical point. And at critical point, why does that meniscus disappears? Because the surface tensions actually drops to zeros, and that is why my densities are same, my pressures are same, volumes are same. So that's why surface tension drops to zero and our meniscus disappears. Now, if I further heat the temperature, what is going, if I further increase the temperature, what is going to happen? The substance is going to be in supercritical region. Okay. Now let's say I am at supercritical region here. I am at some region. I am at some region here. Let's say now I am reducing my temperature again. Let's say I am at here, and I am trying to again reduce my temperature. So what is going to happen? Let's say this curve I obtained. I am here. Then let's say I am at again critical point. So what is going to happen? Just if I pass this critical point temperature, what is going to happen? I am going to see that as I reduce the temperature and as I pass the critical point, what is going to happen? Vapor liquid will be again distinguished from, we can distinguish from each other, so we see a meniscus. So this experiment is performed in a way that first we increase the temperature, we note the meniscus temperature, then we again reduce the temperature, and we again see at what temperature we are again seeing the meniscus. So that average temperature, it should, it comes out somewhere near to this, and that temperature, average temperature, is reported as critical temperature. Okay, is this experiment clear to everyone? I will reduce the temperature and meniscus will reappear, and that will be my critical temperature. So if I experimentally take average, and I can find critical point. Okay, is this clear to everyone? This experiment, it is very easy to understand. Okay, so now let's move ahead for, okay, there are some other diagrams also, thermodynamic diagrams, those are called. So this one is called Muller HS diagram. Muller diagram is called enthalpy entropy diagram. So you see in our, when I was pursuing my BTech some years ago, not some years ago, around some 7 years, 8 years ago. So in our examination, we were given this kind of Muller chart, and we were supposed to find a property of interest, let's say enthalpy or entropy or whatever. So I don't know currently how you are asked in your exams, but we were asked this. So this is enthalpy in some British units. This is critical point. So these are temperature H, T, and I guess this is entropy. It's not written. Yeah, this is my constant moisture percentages, meaning my X lines, dryness lines, 0.1, 0.2. Yeah, these are my constant moisture lines. These are my pressure lines. These are constant pressure lines, vertical lines, and horizontal lines are moisture percentage lines. Okay, so this is very difficult actually. Not very difficult, but you need to see how to do it. So this is Muller diagram. It was for steam. I guess this is TS diagram. No, this is also same diagram. This is TS diagram. This is with entropy. Okay, so with entropy also similar. These calculations actually you need to do when you are solving the problem. Okay, so this is just one glimpse of this kind of two Muller diagrams, HS and TS diagrams. Okay, so okay, so now very important thing, how can we study the PVT behavior of real gases? So there are three ways. One is cubic equation of state, another is compressibility factor chart, and the third one is virial equation of state. So what does cubic equation of state mean? Can anyone tell me? Cubic equation of state. So my equation is cubic. Okay, so cubic equation meaning how many roots I will have of that equation when I am solving it?
Three.
Three roots, right? But how many roots should it have when I am dealing with vapor liquid? Vapor liquid equilibrium region, how many roots should it have? We had a look at that diagram, right? VL, VVN, one insignificant root, that is intermediate root. So we will have three roots. One is one, when I will solve that equation, one root will give me liquid volume. The other root will give me vapor volume or vapor density, however you want to say it. And third volume we will get, that is intermediate volume, where volume pressure both increases, and that pressure, that volume doesn't make any sense. Okay, so let's have a look at Van der Waals equation of state. So this is the Van der Waals equation of state. P plus A into n square by V square, V minus NB is equal to nRT. So can anyone tell me what are the assumptions for ideal gas? First, what are the assumptions for ideal gas? When I am saying that a gas is following PV is equal to nRT. So what are we assuming that it follows PV is equal to nRT? Shruta, can you tell me? Mihika, Harshit, anyone? Okay, so when,
Compressibility should be equal to 1.
sorry?
Compressibility should be equal to 1. Compressibility factor.
Yes, compressibility factor is equal to 1. In 1 meaning it is an ideal gas, but I am asking that, I am writing that PV is equal to nRT. So for writing that PV is equal to nRT, how do I write this? Under which assumptions I am writing it? So this you have already studied, but I will again say. So my first assumption is there is no interactions between two molecules of gases, and the second assumption is volume of gas or volume of a particular molecule of a gas, it is completely negligible to the volume occupied by the gas. So let's say I am sitting in a room. So in room there are some oxygen molecules. So what this ideal gas is assuming that the volume of oxygen molecule is very less compared to the volume occupied by the system. So that is the assumption for ideal gas. So when I am going from ideal to real gas, so I need to try to rectify this assumption. So my first assumption was there are no interactions between molecules. So that assumption I am dealing it by adding A by V square term. So A is nothing but A is presenting the intermolecular interactions present between the gases. So this A by V square, N square you can forget right now because N is just number of moles. So A by V square term, A is representing the number of intermolecular interactions it is representing. And what was other assumption, that volume of molecule is occupied is very less, negligible or negligibly small compared to the volume occupied by the gas. So we need to, this V is volume occupied by the whole system, but we need to subtract this B is volume occupied per mole of gas. So if we subtract V minus NB, so I get actual volume available. So these two corrections are implemented by this Van der Waals. In which year I don't remember. Okay, but in very early years. So from this, this is the basis for any real gas model. So that is Van der Waals equation of state. So let's say A, I said it as A is representing some intermolecular interactions, and B is representing volume occupied, the volume per mole that is occupied by the molecule. Okay, so how can I find this A and B, two constants? Okay, so we know that at critical point, first and second derivative are equal to 0 because it is just merging at a one point. So if I apply this idea, So my equation, this equation at critical point can be written as I am neglecting my mole terms. I am assuming that n is equal to 1. So my PC will be equal to RTC divided by V minus B minus A by VC square. Okay. So let's say I am derivating this first equation with respect to VC at constant temperature TC. So what will I get? With respect to VC, I want to differentiate it. So my RTC will be constant and 1 upon V is nothing but minus 1 upon V square term. And this A remains constant and 1 upon VC square is nothing but minus 2 by VC cube. So minus minus plus. So this term we get. So my first equation, I get it as RTC by VC minus B whole square is equal to 2A divided by VC cube. Similarly, I find a second derivative because at second derivative, this term is also 0. So if I find the term for second derivative, so this is what I get 2RTC divided by VC minus B whole cube is CA 6A divided by VC raised to 4. Okay, so I have two equations and I have two unknown A and B. So if I solve for these two equations, so I get that VC is equal to 3B, meaning my B is nothing but VC by 3. So if I know the critical volume of a gas, then my B constant for that particular gas will be nothing but VC by B. And if I put this VC is equal to 3B in this particular, in this particular equation, so I can also get the volume of A, value of A in terms of PC, TC and VC. So I get my A as 9 by 8 RTC VC. Okay, so I got two constant where B is VC by 3 and A is nothing but 9 by 8 RTC VC. Okay, is this clear to everyone? Is this clear to everyone? Please respond, guys, so I understand.
Yes, sir.
Yes. Okay. So what we did, we derived the constants A and B in terms of VC and TC. But it is better to have, if you remember this meniscus experiment, volume measurement will be difficult, but temperature and pressure measurement will be easier. So what I will do now, I have this equation. PC is equal to this RTC by VC minus B minus A by VC square. So if I put B is equal to VC by 3 and A is equal to 9 by 8 RTC VC. So I get this equation that PC is equal to 3 by 8 RTC by VC, and VC I can get it from here, that 3 by 8 RTC PC. So if I put the value of VC in this equation 3 and 4, so I get my constant in terms of temperature and pressure. Okay, so my A is nothing but 27 by 64 R square TC square by PC, and B is nothing but RTC by 8 PC. Is this clear to everyone why we did this? Because temperature pressure is easy to deal with than temperature volume. So we just did some mathematical arrangements and we got the values of A and B. Okay, so what is what is compressibility factor? Z is nothing but PV by RT, correct? So ZC will be at compressibility factor at critical point will be ZC is equal to PC VC by RTC. So PC is, let's keep it as it is, and VC I am replacing it with this equation that I derived. So what will I get? I get that critical compressibility factor is nothing but 0.375. Okay. Okay. So let's first look at some um, these values for some gases and try to correlate it. Sorry. Okay. Now here. So you see that what is ZC for actual gases? It is starting from here. Okay. So it is 0.286, 0.279, 0.276, 0.26, 0.28, then 0.27, 0.26. Okay, so you are seeing that maximum gases in the list that I have shown it to you, nothing exceptional. Some gases are greater than zero point 0.3, but most of the gases it is falling between 0.2, 0.21, 0.22 to some 0.28 values. Where from Van der Waals equation of state, we are obtaining that ZC is equal to 0.375. So are we able to capture the correct behavior? Can anyone tell me, Mihika? Did we capture the correct behavior of gas by van der Waals equation of state? We can see
No.
that ZC has, yes, we did not achieve because ZC has significant deviations from actual values of ZC that it should have. It should be in some zero point 0.2 to zero point 0.3 range, but from van der Waals we are getting it as 0.375. So we have not these corrections of A and B that we have applied here by adding intermolecular interactions and by subtracting this volume occupied per molecule. So that is not sufficient. Okay. So after that, there are some more equation of states developed so that I will show you from here directly. Those are called Redlich-Kwong equation, Peng-Robinson equation. Uh, s- uh, so those are some complex form of equations. Yes, it will be now here. There is one table. Okay. So, so for that, the equation P is written in some better way. Sorry, where did it go? This equation P is RT divided by V minus B minus A divided by V plus epsilon B, V plus sigma B. This is some general equation or general corrections that we are applying. So for this van der Waals equation of state, the sigma epsilon terms are 0 and omega is 1 by 8. Omega is B was our 1 upon 8 RTC by PC, so that 1 upon 8 is omega here. So similarly for RK equations, we have one term sigma and one term alpha. Then for SRK equation of state, we have alpha as a function of three parameter theory that also includes eccentric factor that we will have a look shortly. And the last one is Peng-Robinson equation of state, in which the constants are different and alpha function is also different, which is dependent on eccentric factor and critical temperature. Okay. So for Peng-Robinson equation of state, ZC is coming out to be 0.30740. So that may be the uh, this is also not accurate, but that is close to the accurate. So there are other equation of states also after that, volume translated Peng-Robinson equation of state, and there are so many equations of state developed after that. Okay, van der Waals was in 1873 and it took 100 years, more than 100 years to reach from 3 by 8 to 0.307. Okay, so you see the real problem, where the real problem lies. Okay. So now let's say these are some rearrangements I am showing that this is my equation P plus A by V square van der Waals equation V minus B is equal to RT. So I am writing A as 9 by 8 RTC PC and B as VC by 3, and I am multiplying both sides by 1 upon PC VC. Okay, so I get this kind of some equation that P by PC plus 3 into VC by V whole square, one term V by Vc minus 1 by 3 second term is equal to 8 by 3 T by Tc. So what we are doing, that P by Pc is nothing but is called reduced pressure. So any property is called reduced property where when the value is divided by its critical property value. So when if I am um, dividing pressure by critical pressure, it is reduced pressure Vc by V, it is 1 by Vr, Vr is V by Vc, so it is 1 by Vr, and T by Tc is nothing but Tr. So I can generate some generalized equation that only depends on reduced properties. Okay. So P by PC, let's say I am dealing it with at P by PC is equal to 2. So for some gas, PC is equal to, let's say, 50, and for other gas, PC is equal to 25. So based on that, we can only we can only see the effect of P. So what does this mean? That I can fix my P and PC. Let's say I will show you that with one example. Again, I will have to go to that appendix. So why this reduced form of equation is very important. Let's say I am dealing at PC is equal to 46. Okay. So my P by PC will be equal to 1 for methanol. So my reduced pressure is equal to 1 for methanol. Okay. Let's say 23. Okay. For N known in my PC is equal to 23. Okay, and let's say my P is equal to 23. So my reduced pressure is equal to 1. So what does this mean? That when my PR is equal to 1, so if I just change my PC, so gas behaves ideally at reduced, not ideally, but we can just have a look at the properties just by reduced. My, let's say PR is equal to here 1, here also my PR is equal to 1. So I can just change the PC and I can get the properties for any gases. Okay, so this is the important for reduced parameters. So this is called two parameter law of corresponding states. By two parameters, it is only dependent on this two. Okay, but this appears to fail near critical curve and it completely fails at critical points, but more or less we can we can have plus minus 5% that is acceptable for polar and slightly non-polar. Generally plus minus 10 is also fine, but that depends on your system application. And for polar gases, their deviations are very high. Why it should be very high? Because this ABC value is intermolecular interaction. So for polar gases, it will be more interactions. So how to capture those interactions for polar compared to non-polar? So those are the real problems. So for that, the third parameter is added to this equation of state. So it is called three parameter law of corresponding states. So what do we say here? Log 10 PR set versus 1 upon TR is plotted. So we see that for simple fluids, let's say argon, krypton, xenon. So this when 1 upon TR is 0.7, I am getting log 10 PR set is equal to 1. But let's say I'm going from simple fluids to water vapor and ethanol. So what is happening? If all fluids were behaving same as same PR and TR, then this curve should be only one curve for all possible gases. But it is not same for all gases. It is deviating from it is not one, it is minus one. I'm sorry. I don't know if I can change it. This is minus one. Okay. So So for water vapor, it is not coming out to be 1, but it is deviating by some particular value. Similarly, for ethanol vapor, it is even highly deviating from minus 1. So how do we define eccentric factor? Eccentric factor is defined as omega. Omega is defined as this minus 1 to minus 1 plus this particular deviations that we are obtaining. So minus 1 minus this particular value, and this value is at TR is equal to 0.7. So minus 1 minus log 10 PR set at TR is equal to 0.7. So this is defined as eccentric factor. Eccentric factor generally gives us the idea of sphericity of the molecule, how sphere the molecule is. So for this argon, krypton, xenon, those are spherical molecules. So that's why for them eccentric factor comes out to be 0. If you put it minus 1 and this one value is also minus 1 for simple fluid, this term is minus 1. So minus 1 plus 1 is equal to 0. Okay, so this question is also generally asked in GATE eccentric factor. Okay. So this third parameter eccentric factor is included. So I will show you again where eccentric factor is included here. So see in SRK equation of RK equation of state, there is no eccentric factor, but in SRK equation of state, there is one term alpha that is dependent on omega. Similarly, for Peng-Robinson equation of state also, so these terms are presented. So by incorporating this omega, we are trying to improve the predictions for real gases. So let's say, I guess omega values are given here. in these tables. So see, we assume that helium should be there, if I know correctly. C, argon omega is exactly equal to 0. For krypton also omega is equal to 0. Xenon is also omega is equal to 0. But for other molecules, you see that omega is not 0. Omega has significant variations, 0.012. Methane is also near to 0, but it is not 0. So methane may behave well without even omega values, but it is near to 0, it is not 0. So there are molecules, so very large molecules, octane, nonane, those are large molecules, so those can't have spherical spherical cloud. Okay, so for them C values are very high. So we are going from methane to octane, nonane, omega is only increasing. Similarly for these isomolecules, isobutane, isopropane, cyclic molecules, benzene also, it is not having 0. Okay, so this is how you can have a real feel of these values. Okay, air is also 0.035, oxygen is 0.022. Those are near to 0, but not 0. So how can you determine eccentric factor by this particular plot? That you need the value of T by Tc and P by Pc. P set by Pc. P set is nothing but vapor pressure. So log PR set is nothing but vapor pressure divided by Pc of that particular component. So from that you can derive these values. Okay. So this was the one part of using cubic equation of state. Now the second part is, okay, is this clear to everyone? It is very easy to follow. Okay, so sorry, where was I? Okay, I was going to show you this Z, compressibility factor. So what is compressibility factor? Can anyone tell me? What is compressibility factor? Harshit, can you tell me? You mentioned about compressibility factor.
PV by RC.
PV by RT. So what does PV by RT means? Compressibility factor Z is nothing but actual volume divided by volume occupied by ideal gas. I don't know if it is mentioned here somewhere, but there are some plots available here. This is omega. Okay, so Z is nothing but PV by RT, but how do we write it in terms of how can we write it in terms of PV by RT? So I will just show you small thing. So Z is nothing but V of actual gas, volume of actual gas divided by volume if the gas were ideal. Okay, so it is V by V ideal. So my actual volume is V and my ideal volume is nothing but, what is ideal volume? Gas, if gas were ideal, so it is nothing but R into T divided by P. So my Z will turn out to be PV by RT. Okay, so my Z values can be greater than 1, less than 1 based on our condition. So I will just show you that plot, but I am not able to find it right now. Z plot is available in this book. So no, this is not Z, this is Z0. Yeah, see, this is compressibility factor versus pressure. So when pressure is very low, so 0 it is 1, but and very near to 0, the pressure is near to 1. But as we are going from, let's say, 0 to 50, so there are significant deviations in this value of Z. So Z is 0.25. This is, I guess, for CO2. No, it is for methane. Okay. So methane does not behave ideally. It is very clear that very low pressure it is behaving ideally, and as temperature is increasing 200 Kelvin, 225, 250, so at very high temperature, so you can see that it is near to 1. It is not exactly 1, but it is slightly increasing from 1. Okay, so gases generally behave at ideally at very low pressures or very, very high temperatures. Okay. Okay, so let's move. This is the one way of doing these calculations. So you should have only the graphs for actual gases available, then you can just find the volume. So it is behaving something like this. Okay, so now third one is our virial equation of state. So what do we say that PV by RT? Those are two terms, pressure explicit form and this one is, sorry, this one is volume explicit form, not pressure. So this is my volume explicit form and this is my pressure explicit form. So in a volume explicit form, I can write my PV by RT as 1 plus B by V plus C by V square plus so on. And for this pressure explicit form, I can write it as PV by RT is equal to 1 plus B by B prime plus C prime P square and so on. Okay, let's say when does gas behaves ideally? Gas behaves ideally at lower pressures. Okay, so my PV by RT will be equal to my pressure is very low. Okay, so this P square term will not be more significant as I'm dealing at low pressure. Let's say I'm at 0.1 bar. So my P is 0.1 and my P square is 0.1 square. So that is nothing but minus 2, 10 is to minus 2. So this term will not contribute more. So at lower pressures, there is a linear function of pressure and temperatures. Okay. So, okay, this is very important thing from your gate point of view. So at very low temperature, you see that it is linear function of P and T. And B is very low temperature, B is negative. And as I am increasing my temperatures, so there will be one case where my B is equal to 0. What does it mean when B is equal to 0? B is equal to 0. That means PV by RT is equal to nothing but 1. So when does B is equal to 0? When my attractive and repulsive forces are equal to same and my B goes to 0, and this temperature where my B goes is to 0 is called Boyle temperature. And in Boyle temperature region, the gas generally appears to behave as ideally. Why it appears to behave as ideally? Because my B is equal to 0. So my PV by RT is equal to 1. PV by RT is nothing but Z. So Z is equal to coming to be 1. Okay, so that's why this is called boil temperature. This is important to know. You may be asked to find the boil temperature, so you don't need any data. You only need ideal gas conditions to find the find the temperature, Boyle's temperature. Okay. Okay. So usually at low to moderate pressures. So the only first virial coefficient is important. So we don't need to go. I explained it to you why, because these terms are not going to uh, contribute more significantly. So only first term is important. So let's say I am dealing with this kind of equation, PV by RT is equal to 1 plus B by V. So PV by RT is equal to 1 plus B by V, meaning BP by RT. So if I multiplied this equation both side with RT by P, so I get that V is equal to V naught plus B. RT by P meaning here only V will be remaining here. RT by P meaning V naught ideal gas volume plus only B. So my B is nothing but V minus V0. What is V minus V0? Actual volume minus ideal volume. It is defined as residual volume. So B is nothing but residual volume at very low to moderate pressures. Okay. Near critical point. Okay, this derivation is important. So when I am dealing with very near to critical point, I can't just go with only first or second virial coefficient. I need to go till at least third virial coefficient. So why do I say this? So we can derive this again. So my PV by RT is nothing plus 1 plus B by V. So I can write P as RT by V plus B into RT by V square. So at critical point, what is going to happen? Del P by del V is equal to 0 and del del square P by del square V, del V square is equal to 0 at constant temperature. So if I find out this this expressions for del P by del V at constant temperature, and if I'm equating it 0, let's say I'm doing it for first equation, so I get that B is equal to minus Vc by 2, and I am second derivative again differentiating it. So I get that B is equal to minus Vc by 3. So for one guess, can I have at one place B is minus Vc by 2 and other place minus Vc by 3? This is not possible. So we are not capturing the true behavior when we are dealing with critical point, and we are only considering my second virial coefficient B. So we need to go at least till third virial coefficient C. So if I add one more term, one more coefficient C to the equation, and if I find del P by del V at constant temperature and del square P by del V square at constant temperature, and if I equate both terms to 0, so I find that B is B and C I can find as B is nothing but minus Vc and C is Vc square by 3. So at very at temperatures near to critical point, or when we are dealing near to critical point, I can't just escape with only B. I also need to include one more coefficient or even more coefficients for accurate predictions. Okay. Is this clear, or do you want me to show the derivation again? I can show it. It's not required. Tell me.
No, sir, it's okay.
Okay. So now one more important thing that we will be seeing through one problem also. So we wrote that PV by RT is equal to 1 plus BP by RT. Okay. So let's say I'm writing that I am multiplying this term with PC and TC. So if I am multiplying with PC, here PC by TC, so I need to do TC by PC and P by T is as it is. So I can write that PV by RT is nothing equal to 1 plus BPC by RTC into PR by TR. Okay. So for non-polar gases, this BPC by RTC term is nothing but B0 plus omega into B prime. So if I put this B0 and omega B prime term here, so my Z is nothing but 1. 1 is as it is. This is B0 plus omega into B prime I am putting here, and this term is as it is. So B0 into PR by TR plus omega into B prime into PR by TR. So this, this contribution is called ideal contribution. 1 plus B naught into PR by TR, that is equal to Z0, and this is B prime, so this is omega into Z prime. So this Z naught and Z prime curves are available. So let's say you are willing to find the compressibility factor for a gas, and if you know these values of Z naught and Z prime from some curve, so and omega is known, so you can directly calculate the compressibility factor, and this correlation is called Pitzer correlation. So it is available in two forms. This B naught and B prime constants are also available, and Z naught, Z prime, B naught and B prime constants are available in terms of correlation, where this Z naught and Z primes are available in terms of values. So I will show you that in the table. So that is called, see here, it will appear, no, not here. Yeah. This Pitzer correlation, Lee-Kissler generalized correlations. So see Z naught and Z1 values are there. So let's take one example using this concept and try to solve a problem for this. So yes, so it is required to store 1000 kg nitric oxide at 131.72 bar and 287 Kelvin in a storage tank. Determine the size of a tank in meter cube using two parameter compressibility factor correlation with Lee-Kissler data. So what is that? What is this saying? This is saying that Z, I am supposed to use Z is equal to Z naught plus omega into Z prime. Okay, and we are dealing with, okay, so TCPC are already given to us. Okay, so to use this chart, to use this chart, what do I need to know? I need to know PR and TR. So for particular PR and TR, I can denote the value of Z naught and Z prime. Okay, so can you tell me first what is the PR and TR for this particular problem? My P is 131.72 bar and PC is 65.86 bar. So what is my PR? Can you calculate and tell me? Can one of you calculate PR and another? Can you calculate TR? Data is here. What is PR? Mihika, what is PR?
Sir, 1 minute.
Yes, yes. And Harshit, TR.
Sir, PR is 2.0.
Okay, PR is 2 and is TR? Can you
So it's
calculate?
1.60.
1.60. Okay. So let's see in this table, my PR is 2. So first I am looking at PR is equal to 2. So here it is not the line where PR is equal to 2. It is stopping at 1. So we need to go to another table. Okay. So in this table for Z0, PR is equal to 2 and my TR is 1.6. So 2 and 1.62 is my this line and 1.6 is my this line. So my Z0 is coming out to be 0.8738. Can you please note it down? My Z0 is 0.8738. Okay. Now to use this correlation, sorry. Now to use this correlation, I have found Z0. Now Z prime is also needed. So similar thing we will do from Z prime. 0.8738, you have noted it, right? Um, Z prime is this. So PR is equal to 2 and TR is equal to 1.6. So I guess it is 0.1729. Yes. So it is 0.1729. See, TR is equal to 1.6 here and PR is equal to 2 there. So it is matching at 0.1729. Okay. So we have two values here. Z naught and Z prime is there. Have you noted it? Both of you?
Yes.
Yes, sir.
Okay, so now what is told to us, our gas is, what is the gas? Nitric oxide. Okay, so now nitric oxide we need to find what is omega. So if I can know the omega, so Z I can find, and Z, as Harshit had told, Z is equal to PV by RT. So if you put the value, you can find the volume of the system. Okay, so let's try to find the omega for nitric oxide. I doubt if it is here. Nitric oxide. Okay, it should be here in this table, right? So let's try to, it should be at the end. Nitric oxide. Oh, great. It is there. What is the value for nitric oxide? I am just highlighting it from here. So nitric oxide, omega is equal to, okay, second column is omega. Omega is equal to 0.583. Okay, so you put the values of Z, Z naught, omega and Z prime and find the value of Z and tell me what are you getting. What are you getting? Z equal to Z naught plus omega into Z prime. This relation, sorry, this relation, Can anyone tell me, Harshit or Mihika, what are you getting? Z?
It is coming 0.8.
Okay. Now what do you need to do? My Z is equal to, you are supposed to find a volume. So my Z is equal to PV by RT. Correct? So pressure is given as, yeah, pressure is given as 131.72 bar. So I will put P is equal to 131.72 into 10 raised to 5 into Pascal in units of Pascal. So I will multiply it with 10 raised to 5. I will put R is equal to 8.314 and temperature is given as 287 and Z you calculated. So what do you get as your volume? You just put Z is equal to PV by RT and tell me what is the volume you are getting. So that will be the total volume of system. Then we need to multiply it with moles. So first tell me what is the volume you are getting.
Sir, final is B answer over.
Yes, final answer is B. It is not exactly B, but it is near to. What is the volume you are getting?
Sir, I am getting almost 5.217.
Yeah, exactly. Okay, correct. So you just need to multiply your volume with moles, 1000 kg of nitric oxide divided by the molecular mass is given. So that will give you the moles. Okay. Is this clear to everyone? Harshit, were you able to understand?
Yes, sir.
Sure. Okay. So there is one more problem. We can do it. Yeah. Okay. This is easy. So we can do it. So this says that volume of 2 meter cube is filled with 7 kg ammonia at 300 Kelvin. So volume of system is given as 2 meter cube and mass is 7 kg of ammonia. Okay. So and temperature is 300. So determine the pressure exerted by ammonia using ideal gas law. So what is my ideal gas law? Ideal gas law is P into V is equal to nRT. Pressure I do have to find. V is 2 meter cube is given. Moles you can find 7 kg ammonia divided by what is the molecular mass of ammonia, that is 17 kg per kilomole. So you can convert this, you can find the number of moles and R is 8.314, temperature is 300. So what is the volume that you are getting? It is simple, PV is equal to nRT you have to do. What is the value you are getting? Harshit, Mihika, anyone? If done for ideal gas only. Okay, so it is coming out to be 0.511, where P is RT by V, R is 8.314, T is 300, and my molar volume will be equal to 2 is actual volume divided by my number of moles. So 7 kg mass divided by its molecular weight, 17 into 10 raised to minus 3 kg per mole. So if you put this, you get ideal gas volume as 0.511 into 10 to 6 Pascal. So that is nothing but 0.511 megapascal. Now, second point is using van der Waals equation of state. So what do you need to do? P is nothing but RT divided by V minus B minus A by V square. Correct. So B is given as 0.037 into 10 to minus 3 meter cube per mole, and A is 422.4546 into 10 to 3 minus 3 Pascal per meter cube mole whole square. So if you put these numbers, B is R into T divided by molar volume was this minus B 0.037 into 10 to minus 3 minus A value divided by V square. So you get that volume is coming out to be approximately 0.499 megapascal. So for ammonia, this is not a the pressures are more or less coming out to be same. It's not a huge change using van der Waals equation of state. Okay, is this clear to everyone?
Yes, sir.
Okay. So thank you so much. We will meet next week. So if you have any query, please feel free to write me here. So we can, I will try to resolve it. Okay. So thank you so much. Till then, enjoy and bye bye. Thank you.
Thank
Thank you, sir.